Welcome back to ECE 442-542. We are beginning now Unit 5, and what we want to do is remind ourselves where we've been, and that's with respect to modeling in the discrete time setting and z-transforms, both z-transform and inverse z-transform. That's Units 1 through 4, and where are we actually going to go with the remainder of the course. Where have we been? Well, we really started learning how to model systems and waveforms and how they interact in the time domain and the frequency domain. In the time domain, we had difference equations, and in the frequency domain, we have transfer functions. And we learned how to solve difference equations similarly to how you learned how to solve differential equations in a differential equations class. We can look at equations that are non-forced or homogeneous, initial condition type problems. And we can look at and know how to solve difference equations that are forced. So we know how to work with systems described in the discrete time setting, both in the time domain, frequency domain. We can do the solutions by maybe transforming into the frequency domain, multiplying the system times the waveform or pieces of the waveform, get that z-transformed output expression, inverse z-transform, and now we have the output expression. We know how to play now with difference equations or discrete time systems. We also understand this idea of a sample period or sample frequency. They are related by omega sub s is equal to 2 pi f sub s. Those omega sub s and f sub s are both sampling frequency. One has units of radians per second. That's the omega sub s. F sub s has units of hertz or cycles per second. Those are related to the sample period by 2 pi over t, or we know that the sampling frequency in hertz is the reciprocal of our sample period. 1 over the sample period, which is sample period has units of seconds per cycle. Now we invert that and we get cycles per second. We can relate that sample period or sample frequency to the highest frequency in our system, which we're labeling as omega c. Since we're dealing in a control environment, we want to make sure that we capture a lot of the intricacies of that signal. So we actually want to see or to sample at 30 times the highest frequency in our system or in the signal that we're sampling. And that 30 omega c could be closed loop bandwidth. If you're just concerned about a system without worrying about changing its speed or its behavior, then maybe omega sub c corresponds to the highest frequency of your open loop system. We've learned how to do the z-transform, and that could be two-sided, it could be one-sided, it could be right-sided, it could be left-sided, depending on the index n and where that n is supported. Is it supported for all values of n from minus infinity to infinity, or is it supported only for negative integers, or is it supported for non-negative integers? We can find the z-transform in any of those settings or scenarios. We also know how to map between the s-plane and the z-plane by understanding that the frequency variable z is equal to e to the st, where s is the s-plane frequency domain variable and z is the z-plane frequency variable. We have these two complex frequency planes, one s, one z. S is for continuous time systems, z is for discrete time systems. We can then go back from the frequency domain back into the time domain by means of the inverse Z transform. And why do we need the transform and the region of convergence? Is it important to have both of those, or why do we say we need both the transform and the region of convergence? If we didn't have the region of convergence, I could actually give you a time domain sequence that's consistent with the transform that you've supplied me with to be either right-sided or causal or left-sided or anti-causal, depending on where it starts and in the time domain. But to have both the transform and the region of convergence is important, because now that tells us uniquely how to determine which of these sequences. If I could, from one transform, supply you with two different sequences, how do I decide which of those sequences corresponds to that transform? Well, you can't unless somebody gives you, in addition to the transform, the region of convergence. And you know how that's related relative to these pictures. If I gave you this leftmost figure, I now have a region of convergence that's unbounded. The z-plane, or the region of convergence, is going off to infinity, and the poles are inside that region of convergence, or interior to the region of convergence. What kind of a waveform corresponds to this particular pole region of convergence pattern? We now have the fact that this point, we could allow this z to go off to infinity, and if you remember the series expansion structure for x of z, you now have x of minus 1, and this could be dot 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 plus z to the 1 plus x of 0 z to the 0 plus x of 1 z to the minus 1 plus dot dot dot. If z is allowed to go off to infinity, and we know that x of z is a bounded transform expression, then for that case we cannot have any of these terms. Because if z is now z or z squared, and z is going off to infinity, that would cause capital X of z to go unbounded. That means for this pattern on the left, this corresponds to a causal waveform. And if, in fact, we did something a little different, and we said, oh, what if we don't allow that to go off to infinity, but now we bound that region of convergence and don't let it stretch to infinity, then we could pick up a few of these, a finite number of these terms in our series. Then we would actually have a right-sided sequence. What about the middle region of convergence? This is really the complement of what we just saw. Now we could look at this expansion and say, oh, z equal to 0 is a part or belongs to that region of convergence, and all of these terms now have to not be present, or capital X of z would go unbounded. Or in this case now, we have an anti-causal waveform, and if in fact we removed that point at, I don't know what color to make that. Why don't I make it sort of this black? If we actually removed s equal to 0, so s equal to 0 is removed from that region of convergence, then we actually could have a finite number of these terms that are powers of z to the minus 1, z to the minus 2, etc. We could have now a left-sided time domain sequence. If we now have the rightmost region of convergence with the poles indicated here, and realize in all of these patterns the poles are never on top of or belong in or to the region of convergence. In this case we have a two-sided sequence in the time domain, because s equal to 0 is not belonging to the region of convergence. I'm sorry, z equal to 0 does not belong to the region of convergence. Z is not allowed to go off to infinity, so our region of convergence is bounded. Now, in fact, we could have a two-sided time domain sequence. Where else have we been? Well, then we started worrying about discrete equivalence. We can talk about those in the time domain setting or the frequency domain setting, dealing with state space representations or transfer function descriptions. We had two different scenarios. Scenario number 2 was actually the zero order hold, where we collected the zero order hold properties together with the plant g of s, and we found in the frequency domain that the zero order hold equivalent, capital G of z, is now 1 minus z to the minus 1, that factor times the z transform of g of s over s. And remember, now we have transform tables that we could look for something in the Laplace column that has a structure like g of s over s, or if you now partial fraction expand that, can you now find the appropriate expression in that specific factor? Then you can immediately take this z transform expression by staying in the row of that z transform table associated with Laplace transform. It has its corresponding z transform pair. You could also work in the time domain to find a zero order hold equivalent from a continuous time system that's described in the state space form or has a state space representation. You would now find e to the capital AT, or that would be the system matrix, and gamma would be the input matrix in that zero order hold equivalent. You can also have the numerical integration strategies where we talked about, how do we add on this additional sliver of area to our overall sum. Now we have doing that looking forward from the previous time, or looking backward from the present time, or now how do we average those two time points with the trapezoidal or the bilinear or the Tustin, depending on who's naming that third property of numerical integration. And with respect to discrete equivalence, we can also talk about pole zero mapping, and there it's important to understand this concept of zeros at infinity, or that's now connected to the pole zero excess, and that has then direct connection with the implementation concerns. If you do not have access to the present input, or it takes a lot of time computationally to generate the output once you have the input, then you might want some delay between when you have the input and when you present the output from that expression or system. So you might actually want zeros at infinity in your transform domain, but we've been concentrating on the zeros at infinity in the S domain to allow us to actually capture how many z plus 1 factors we introduce in our discrete equivalent. Let me just do an aside, because we have had some students ask about zeros at infinity and can we have a negative number of zeros at infinity. Let's try to look at that and just remind ourselves again where we have been or where we are at now. G1 of S, suppose that's now k times s plus a over s plus b, s plus c, s plus d. Now somebody might say, okay, G1 of S has how many zeros at infinity? And you can look at G1 of S and you can say, oh, it has, in terms of number of poles, it has 3. It has how many finite zeros? These are finite values of S that cause G1 of S to vanish. There's one of those. So you now have a pole zero excess of 2. So the zeros at infinity, and I don't remember if this was the notation. I guess spring recess was too long. But let's say we label the zeros at infinity as I sub z. Then that's actually equal to the number of poles minus the number of finite zeros, or 2. So we do have 2 zeros at infinity in G sub 1 of S. What if now, the next question that is being asked by some, and maybe it's in everyone's mind and they just haven't decided to ask it, the question, what about G sub 2 of S, where G sub 2 of S is now k s plus a s plus b over s plus c. What do we do there? Or what happens relative to this concept of zeros at infinity? Well, in this case, there are no zeros at infinity. That's what we will agree to conclude or state. And in fact, we can actually look at this a little different way. And let's do some circuit analysis with cadence. I don't really want to do that. So let's not do that, since I now have too many windows open. But now we have G sub 2 of S. If we look at that, we actually can see that we have upstairs, as S goes to infinity, we have S squared dominating, and downstairs we have S dominating. So now we have, as S goes to infinity, S squared over S, or this is now approaching, as S goes to infinity, G2 of S is looking like S, or K times S. Well, what's that doing? What's G sub 2 of S doing as S goes off to infinity? Well, G sub 2 of S is blowing up, and that was how we defined poles. When G sub 2 of S goes unbounded for those values of S, that's what we called a pole. So in this particular case, for G sub 2 of S, we could say there is one pole at infinity. So instead of worrying about negative number of zeros at infinity, let's just call those poles at infinity and call it good. So in this case, we have two more zeros, finite zeros, than we have number of poles, and for that reason, now we have poles at infinity. As we let s go to infinity, that g sub 2 of s expression will go unbounded, so we now have a pole at infinity. And there's no need to keep track of negative numbers of zeros at infinity. That's where we've been. Where are we going? Well, what we want to do now is start putting all of that together. We've learned how to build g sub z, capital G of z, by zero order hold equivalence. We also know how to create a C of z. If somebody gave you a C of s, you could find the discrete equivalent using numerical integration strategies or pole zero mapping. But now what we want to do, suppose you now are given a G of s and somebody says, I want you to control that, but I want you to control it with a digital controller. You could now find a zero order hold equivalent for that G of s to obtain a G of z, and now you need to learn how to design capital C of z. How do we determine what capital C of z needs to be? So in fact, what we want to be able to do is design this C of z, which is really, we can call it a compensator or a controller. This is what we want to be able to do in the rest of the class, is figure out how do we design this compensator or controller or this capital C of z. And in order to do that, it might be helpful to actually know or understand what's going on between the reference input R and the output Y. It's going to obviously be influenced by G of z and C of z. But you could now find, based on if you now are given or if you've designed a capital C of z and you know what your G of z is, you could find the transfer function between R and Y. You now know what capital T sub C of z is. That's just the transfer function between the reference input R of z and the output Y of z. In order to find a capital C of z, it would be helpful to know what are some desirable closed loop transfer functions, or what closed loop transfer functions actually have the behavior that we would like our system to possess. So now we still need to figure out how do we create or produce this desired closed loop transfer function. Maybe we have a G of z. We now, maybe our boss, she says, I want you to have your system behave like this desired transfer function T sub C of z. Well, how did she come up with that? Well, that's what we want to be able to do. We want to understand how do we create or determine what these ideal or desired closed loop transfer functions need to look like in terms of their poles and their zeros and gain properties. How do we make that happen? So what performance, and that's really the way that we will find these capital T sub C of z's, is going to be based on the performance behavior that we want. Maybe we want the system to respond with a certain settling time, or maybe we want it to have a particular overshoot behavior. Maybe we don't want the overshoot more than 10%, or maybe we want it to get to our peak value very fast. So what is the rise time or the peak time? Those are some performance characteristics that we might be wanting our desired closed loop transfer function to possess. So we now need to be able to being given performance specifications, can we now translate that into a desired closed loop transfer function and use that now to maybe specify our controller capital C of Z? And that's where we're going.